Okay, so let's just continue. And it's hopefully today I'll have less technical difficulties. I can't imagine any worse. Okay, so today I will continue to talk about molecules in tweezers and single molecules. And in particular, I want to start turning on their interactions and entangle them. Okay. So just a reminder, we all know we want to use the molecular resources, actually all the degrees of freedom, and a key element in addition to the degrees of freedom is to utilize the intrinsic dipolar interaction. Okay, so last time I skipped this slide, but this time I'll just go a little bit more in detail to give an example. This is more like a proposal, but and then actually elements of this have been realized. So we're thinking about molecules for quantum simulation and computation applications. And we really want to use, like where we see molecules is advantageous is that it's complex, and of course we know it's hard to control, but once you get it all under control, that these intrinsic coherent degrees of freedom, we call these coherent degrees of freedom qubits, that can be tailored into multiple requirements. And as examples, for example, we often want a qubit to store information without being perturbed, while we also need gate interaction to perform logic gates. And these are sort of intrinsically competing requirements. How do we realize in one system? We realize them, we could realize them in different degrees of freedom. For example, high-profile nucleus beams are very good, robust qubits, not very sensitive to environment. But we want them to interact, and the interaction will come through the form of dipole-dipole interaction through this resonant dipolar exchange. I'll elaborate that a little more. And going from one degree of freedom to another degree of freedom, actually there are intrinsic molecular coupling, in the form that you will show in calculation. You can find these coupling, and then you can bring fluid information from one degree of freedom nominally, like initially in these manifold, nucleus beam manifolds of the rotation ground state to the rotation first excited state, for example. Okay, and already, as has been demonstrated, for example, in Simon's lab and other labs, that nucleus beams are really good for information storage, are really great qubits, and they've shown coherence time, basically, I think they say infinite. Yeah. And, this decay is due to molecule loss. And the rotation degrees of freedom has also been shown to be very good. Not as good yet, but I think Simon's going to tell us some new result, which is very exciting. So in this demonstrated work with calcium fluoride, we can have coherence times on the order with spin alcohol 100 milliseconds. So both degrees of freedom can be very coherent, and that's what we like and what we know about molecule, and we just need to work to have that. Okay, so now in order for that to turn it into a logic gate, in particular the gates that we're thinking about is called I-swap gates. It's the kind of sequence we were first envisioned is in the following way. First, we're thinking about, tweezer array of molecules, and then there's some kind of storage zone, there's some kind of gate zone. We can bring, because these tweezer are very easy to move these molecules around, we can move the molecules and then prepare them in a sequence to prepare them in the right rotational states to interact via exchange interaction and then bring them back out and then eventually get that back to the storage room, into one. And the nice thing is that we could basically implement these whole sequence. So first, if we were to store information, if my 0 and 1 were to be in the nucleus beam states, they're not interacting between the two qubits. In order for them to interact, we bring them into the rotation excited state, and while also changing nucleus beam state, and that's possible because of this molecular coupling. And the storage qubit, things that are far away, we can light shift it away on this microwave transition, and therefore they're not being transferred into the rotation excited state, and that way we can have this side selected addressability, as I'll show that we can demonstrate that as well. Okay, so we can do a pi pulse to go from the 1 state to the rotation excited state, and then do wait just the right amount of time for dipolar exchange interactions, and then bring again whatever the result of that back down into the 1 state in a global pulse while shifting the storage qubits of resonance to complete a sequence of I swap gate. And here is okay. Before I get into the truth table here, the important thing here, for experimental consideration, is that all the states are field insensitive. These are the molecule we're considering doesn't have electronic spin, so it's basically just nucleus. They're also the nucleus spin state, so B field insensitive. They're long-lived, and these interactions occur without us polarizing the molecule in the laboratory. And that's important because, or at least the way that I think it's important, is because usually when you polarize the molecule in a laboratory frame, often for these kind of molecules, you have to exert quite large electric field, and that gives rise to a very large DC starch shift of the energy level of the molecule itself. It could be like megahertz, gigahertz, while your interaction is only on the order of kilohertz. So you will have to control that electric field very, very well if you really turn on to have kilohertz interaction, polarizing the laboratory frame. And therefore, we don't require that. Actually, in fact, we want to work in 0 electric field, and these dipole-dipole interaction are the transition dipole, as we quickly sketched out last time. So in the absence of electric field or no dressing field is where we like to work. Okay, so now the truth table is over here. The sort of the important thing is after the sequence, we get 0, 0, go to 0, 0, 0, 1, go to I, the imaginary number I times 1, 0, 1, 0 go to 0, 1, and 1, 1 goes to 1, 1. Okay, and this, a swap gate will be 1, or 0, 1 go to 1, 0, and 0, 1 go, so 0, 1 goes to 1, 0, and 1, 0 goes to 0, 1. And that is not entangling because that will be a product state. So this space factor of I is actually very important. And that actually is the reason why we. So let me just illustrate that one very quickly here. And I think most of you probably know this, but it doesn't hurt to have one line of mass to kind of illustrate this point. So what does it mean for some two particles to be entangled? The state of that of the two particles is not separable. If it's separable, if it's the product state, it can be written as a product state, then the two particles are not entangled. So if we have, say, start with the superposition of all of this, for example, 0, 0, 0, 1, say that's my, I can have an arbitrary superposition, then we can say the equal superposition to start with. And after my gates, if I end up being, after my gate, if I'm just doing a swap, which is non-entangling gate, then what I have is this, right? So I'm just basically swapping this, and this can be written as a superposition of 0 and 1 of the first qubit. Well, I'm not going to worry about normalization for now. And product with superposition of 1. Sorry, the second qubit being 0 and 1. Right, so it's a product state and therefore not entangled. Okay, and now if we say, okay, well, what about if I have a minus sign here? Okay, well, I start with this, and then my gate give me a minus sign of a swap. Well, it turns out if I have a minus sign, then I can still factor into this, right? I can still factor into this. And therefore, it's still not an entangling gate. So these guys factor that as well. Okay, so that's still not an entangling gate. But if I have in this case, I have an I here. Then I couldn't factor because if I put an I here, then ultimately this one. So you see that. Therefore, in this case, if this is what I get after my entangling gate operation of my I swap gate, I cannot factor in this case because this will have a different state. So this is the important part for designing a gate. You know, you have to have a truth table that ultimately gives you some non-trivial phase that you ended up with a state that you cannot factor. Okay, so then it turns out it's also quite easy to get this I swap in a way that any coupling, you know, any two-level system with these kind of coupling, you can actually readily get these kind of gates. Okay, and I'll illustrate that in a little bit. Now, what I'm talking about here is dipole-dipole interaction, the same form that we wrote down, the same form that John gave us. You know, I'm carrying this 4 pi epsilon naught because I'm an experimentalist. When I put in Mathematica, I like to carry that. And in the absence of laboratory polarizing electric field, we can write this in the form of spin models. And I know Timur is going to talk a lot more about actually going into more details, but I'm just going to simplify and say, like, this is the coupling Hamiltonian that I care about, which is the same as I wrote down, basically similar to the one that I was considering yesterday. So what we end up with is S plus or D plus. I mean, if you think S is the D, S plus, S minus, S plus. Okay, and then the additional term usually you will have SD, SD. That is 0 because we are not polarizing them in the laboratory. Okay, so this is the coupling that we're considering. And if we write down in the basis, and now we're only considering rotation because this is the part that entangles. Okay, so we're not worried about the preparation pulse that prepare the hydrogen, prepare the 0 and 1 in the hydrogen state. But by 0 and 1, you can then imagine to be just the rotation. Good. Then this Hamiltonian basically just contains off diagonal coupling term between the 0E and the E0. You know, the ones that has opposite parity state. And then we can do a unitary evolution. So e to the minus IH T over H bar. And that just gives you actually the non-trivial part is giving you the part in the middle. And then if you wait, for example, you know, omega T is equal to pi over 2, for example, then if you start in these one state, you know, 0E or E0, then you apply this unitary evolution, then just, you know, say you start with 0E or E0 after the unitary evolution, you'll get you'll get this plus I 0. There we go, 2, the normalization, and this is the delta. This is the delta in the sense that, you know, the first qubit if the first qubit is in 0, the second is in E, and then if the first qubit is in E, the second is in 0. So if you just wait just the right amount of time, then you have a maximum the entangled state, which is the belt state. Okay, and then this is just, also possible sequence to prepare that. Okay, so you can see that it actually all comes from the fact that if you have two things that are both, and then in this, and then you had a non-trivial time evolution, then you can go. Okay. All right, so that's what, you know, that's so that's sort of the you know, this is how we will utilizing dipole interaction to entangle two molecules. Well, I previously gave you, you know, we want these 3 levels to achieve what we want. You know, really just 2 levels enough to entangle. The 3rd level was we want to separate the test. You know, formation storage for gates. Other ways of, you know, not allowing the molecules to move around when they put in the nucleus space. In addition to putting in the nucleus space, you can also just separate them in parts. Dipole interaction involved now one over R2, and therefore they also don't interact very strongly. So that's another way. But when we first considered this schemes, we were, you know, trying to be thorough, and then we also considered the full relevance of the energy landscape. And of course, for these sodium molecule, there's a lot of nuclear spin states, so make the realistic picture a lot messier than the 3 states that I drew. But nevertheless, you can find the levels that you want to achieve, the couplings you want, and to achieve to achieve, you know, basically, you know, to achieve with state preparations. And without going into too much detail, the real limitation for these kind of gates would be ultimately that these energy levels are very close by, and therefore they impose a speed limit. Okay, because you can leakage. When you exchange, you can exchange to the wrong states because the energy level is a bit close. So that gives you an absolute sort of time scale, depending on the energy separation. And when we first consider a very small sort of magnetic field, we could say, like, you know, if you can bring them very close, you know, something on the order of less than a micron, a little bit less than a micron, then you can have a gate time on the order of 50 microseconds. But with a limitation that this is, you know, this could have the potential of population leaking out of the initial state that you want. But we are now working at much higher magnetic field in our experiment. Our Feshbach resonance at 865 Gauss. So this is actually, this number is improved significantly in the sense of the Zeeman energy levels are much more split, and therefore the speed limit is the imposed speed limit is much lower. Is that right? Yeah. Okay. Any question about this? Good. Okay, so now last time I introduced the 2 approaches, you know, kind of compare and contrast the 2 approaches, and I focus on the part here today. I'll talk on both approaches. I'll continue talking about both approaches. And this approach of assembling molecule from single atoms, the punchline last time is that through this Feshbach association process, which is mapping basically all the atomic control to the molecular control through the magneto association of this, and mapping of these degrees of freedom. Ultimately, we have molecules in a single internal state, predominantly in a motional ground state, so sort of between 60 to 70%. Now, from Feshbach molecules, we can, you know, what Simon introduced already, you know, do a 2-photon coherent transfer to bring them all the way down to the low vibrational ground states. And this is a specific theme for sodium cesium that we utilize. We had to make sure, you know, initially we're working with single molecules. Now we have an array of molecules. We had to make sure our beams are more uniform in this kind of top hat geometry to match the dimension of our array. So we can shape the beam with this airy beam shaper, so passively shaping. And we can use actually the two Raman transitions, so two photons shining out simultaneously, pulse on for a certain duration to get coherent Rabi oscillation between the weakly bound spot space to the low vibrational graph. And these are sort of the 5 individual side data. Okay, and the lifetime of these molecules exceeds more than 3 seconds, and we're gonna go check beyond that. Because experimental cycle times are fast, so we don't really want to slow our statistics down. This is probably, I mean, probably is longer than this, but like this generally is limited by photon scattering. Okay, so with individual molecule fully controlled, then we're now ready to manipulate their rotational states to allow interaction, is what I just said, and again to remind you what we're utilizing the dipole interaction is this flip-flop and effectively flip-flop interaction, and that means we want to compare molecule, adjacent molecule state, for example, in different initial states, and then see these interactions in these flip-flop interactions. Okay, and then this energy level is on the order of gigahertz separation. Now, this actually, a resonant dipolar exchange interaction has been observed in molecule in actually now a couple of different systems, and I'll go through them quickly. And first, it was 2013 in the KRB experiment in July, where in this sort of sparsely filled optical lattice of KRB molecule, they were able to see dipolar interactions for these oscillations showing up when they prepare superposition of molecule in 0 and 1 rotational states. The control continued to improve in the July experiment. In their second generation apparatus, they had very fine electric field control, so they can turn on electric field and turn on electric field gradient such that they can address particular layers and prepare them in a particular, for example, angular 1 here and angular 0 here, angular 0 there, and then they can see, as shown in this picture, that the dipole interaction between layers can change. For example, in this case, 0, let's see, 0, 0, 0, they don't see anything going on, some phase rate. And then if they have 0 and 1, then they see someone goes to 0, 0 goes to 1 in a different layer, and that has a consequence of collisions, faster collisions that leads to loss, and that's their probe of these dipole interaction. And then when they prepare 0, 1, 1, once at 1, 0, 1, then they see the rate goes up factor up to. Okay. Now, what about individually? Where we continue to push the controllability. Before I get to talk about our individual control, just wanted to mention another experiment, which is in Princeton, where they now have quantum gas microscope of molecules, looking at individual molecules here, and they also see dipole interaction. Again, sparsely filled molecules in lattice in 2 dimensions in this case. Okay, so the site select addressing is what we want to prepare molecule in 1, 0, 1, 0, 1, 0 in rotation 1. This 1, 0 are the rotation state. Okay. But generally, as I mentioned previously, that these microwave 3.5 gigahertz are very long wavelengths, so on the order of 10 centimeters. So you couldn't really distinguish molecules in different tweezers, which are only separated by micron sort of separations. But again, these molecules are extremely sensitive to electric field, and in this case, oscillating electric field will start shift from the optical tweezer itself. So we can measure this in some experimental units that these start shift could be on the order of megahertz. So they're actually extremely large, and And therefore, we can utilize it, for example, by patterning, more intense and less intense, or more intense, less intense, these alternating patterns, we can shift this 0 to 1 transition, and therefore prepare our molecule in 1010 to a global microwave pulse, but with the individual pattern of the intensity. Okay, but with megahertz intensity, with megahertz shift, you can immediately, you probably immediately worry that's going to cause a lot of problem for the coherence of if we were to prepare superposition of states. So the most recent thing, sort of along that line, is that we actually have another set of tweezers that we're not using once we create molecules. These are the original sodium tweezers, so we can pattern these intensity, patterns that we want, using this separate tweezer and then just turn it off once we do the state preparation. So there are these techniques. Okay, so the light shift cause decoherence is sort of the major issue, and that's something to be addressed, so that we can enjoy the intrinsic coherence of the molecule. And this is for both single body coherence, if we prepare superposition of say 0 and 1, this levels are shifting, that's problematic. But also the fact that if we want the two molecules to interact, if the energy level are not in resonance, then that also, makes that interaction weaker. Okay, so light shift, it needs to be controlled. That's sort of one of the biggest, I would say, one of the biggest challenge for trapping single molecule in tweezer, because tweezer in generally is very intense. This actually is different, depends on the structure of the molecule, as I mentioned a little bit later. But ultimately, light shift is an issue with these tweezer trap molecule, because we just can't come up with that. So we can measure, we start with linearly polarized tweezer beams, and we can measure these n equal to 0 to n equal to 1 transition as a function of trap depth. And then this way we, I previously say that it's on the order of megahertz for a trap depth. Actually, I have the exact slope here. Megahertz trap depth, so that's the depth of, the depth of the trap, and the start shift, the differential start shift between the n to 0 and n to 1 can be on the order of 200 kilohertz. So very, very large when you think about it, comparing to dipole interaction, which would be on the order of kilohertz. Okay, and this is what we want. We want something that's like this, where the slope will be 0. Obviously, then there's no differential structure. So Simon had already mentioned a little bit about these polarizability of molecules. And so where does this differential structure comes from? It turns out molecules, the atomic molecule, we can, visualizing this picture, has these different polarizability depending on whether we polarize them perpendicular to the axis of the molecule, or perpendicular or parallel. And these values can be, calculated from Olivia's Deleuze paper. But in general, for example, so the NCCN, that this parallel polarizability is 4 times bigger than the perpendicular at the wavelength that we care about. And this is intuitive because, molecules dipole moment is this way. So you can imagine, like, this makes a lot of sense that this is a lot larger than the perpendicularly polarized situation. And for n equal to 0, we actually have, basically is a spherically symmetric state, and the total polarizability is just the sum of, this direction plus this direction plus that direction. Okay, but for n equal to 1, the eigenstates are these p orbitals. If we were to line that up, let's say on the xy axis, xyz axis, then they're really different if you have some kind of polarization direction. You have some quantization axis, let's say, pointing in the X direction right now. So this is parallel, so this is going to be, have a large shift, while these are going to have smaller shift. And most of the work in prior cases have chose the quantization axis to be at an angle such that you had just the right mix between the parallel and the perpendicular direction. So that when you make a transition, this is the magic angle that allow you to make it, to have the same polarizability and therefore nulling out these differential shifts. Okay, but in the strong light limit, not so strong like pulse laser, but strong in terms of it become the quantization axis. Then as we turn this angle of turn this polarization of the light, molecule just tracks it. Okay, and therefore we don't have this independent control of, another quantization axis and our polarization axis would be a particular angle relative to that. Okay, so we have to have a different solution, and we thought about this. This is one solution that is to use magic ellipticity. Okay, by that we mean we will again have the right mix of perpendicular and parallel components of our light polarization, and with just the right angle, the right mix. And let's see, this is always perpendicular. But in this particular situation, we will have just the right mix. This will be kind of flipping between the alpha parallel and the alpha perpendicular, so it's not the right mix. But in the middle, this one will allow us to have the same polarizability as the ground state with this combination of parallel and perpendicular situation, and therefore this should allow us to know how the differential light shift. Okay, so this is a calculation as a function of track depth for the three different kind of eigenstates. You see that if we transfer to this state, we do expect to have zero, to minimum sensitivity to the light shift. Okay, but this also means that we had to have an ellipticity to our tweezer polarization, which is not so trivial. So we implemented by putting in a quarter wave plane right before going to the microscope objective. That is that allow us to have different polarization of the tweezer at different part of the experimental sequence. Sometimes we need to have linear in a particular direction to allow sideband cooling. And then once we make molecule to parallel rotation states, they need to be in this magic ellipticity to allow nulling out all the differential light shift. Okay. So this is the spectroscopy we perform. So for this particular state, you can see the light shift is nominally zero. These other states we can also couple to, they have strong light shift. As a function of two different track depth, these are track depth. We can measure as also as a function of these rotation angle that we can tune very finely. That's triggerable. And where they cross is where the differential light shift is zero. Okay. So how well, zero is never zero. So how well do we do? We now have a magic electricity that allow us to reduce the light shift by a factor of 2000. So it's 100 hertz per megahertz track depth. Okay. Our Renzi, so our coherence time, single body coherence time is increased, but not increased as much as we had hoped, and we're still trying to figure out why. So there may be some other limitations. So we should be able to hopefully get to this number after 2000. Okay, so we work with an array of molecules. So some limitation could come from that each site are slightly different because the beam comes in at a slightly different angle, and they're by infringing materials in our beam path. we characterize that a little bit and by actually turning up our trap depth to be even larger so that we can actually see site to site variation. And that would be on the order of kilohertz for these kind of almost 10 megahertz trap depth. And for dipole interaction, we will reduce down to the trap depth much less to have much less than a dipole interaction strength kind of interaction variation. Okay. So now with that, the next thing is to bring two molecules side by side for interaction. It turns out there's something peculiar, which is this anisotropy aspect of the molecule that we also need to consider. So it turns out these molecules that we prepare at this magic ellipticity in the laboratory turns out to be also with their vector angle relative to the dipole direction to line up right exactly at where the dipole interaction is 0. Okay. So that means in order to actually have dipole interaction away from 0, we need to change these quantization axes in the laboratory frame, which means we will need to put in also a halfway plane, tune it to, basically it allows to from -2 units of dipole interaction to 1, and then changing stuff. So that's something that we're working on. So we are expecting these dipole exchange time scale on the order of milliseconds at sort of 1.7 micron separation. Okay, so we're actively working on that, but we're also looking ahead to figure out ways to enhance the interaction between two molecules. So this is in this diagram, we show, if we have a molecule here, a molecule there, from here, they have a dipole moment of 4.65, which give us on the order of millisecond time scale of interaction if they're microns apart. But getting them close is not so easy in general, and that's sort of at the limit of how fast we can go. In order to go faster, if we want to, break into the microsecond kind of time scale, for example, we can consider having a reaper atom in the middle. So this is an atom, the ground state. We can go to the reaper state, and the reaper sort of opposite parity state, for example, S and P or D, or so on and so forth. You can find states that match that energy levels with the rotation states of your molecule, and that dipole moment turns out to be 10,000 times bigger. So for example, 10 kilodivide between this particular choice of medium reaper atoms. And we can also show that if we basically mediate the interaction with a reaper atom in the middle, when you drive, if you basically a truth table is a slightly different to the logic gates. This table here, you could also have this non-trivial phase factor, which in this case is in part a minus phase factor in the 0,0 case for non-part. The other states we swap it because the phase factors are 1. And this way will also allow us to entangle the two molecules that are separated, but with much faster time scale, effectively increased by the factor of this intense dipole moment of the reaper. Okay. So on that front, we're working on just showing some of our reaper systems. We have, I showed this picture at the very front. When we start with a stochastically filled array of atoms, we can, for example, arrange them to a circular shape for study physics with periodic boundary conditions. We can excite reaper, CCs and reaper into reaper states, depends on whether they are really close by. These are just added in a molecule close by, or at single isolated one. We can have these coherent Rabi oscillation between ground and excited state, but the close by here we have these reaper blockade where these oscillations are about square root of 2 faster. Okay, so just need to integrate it all together, basically shining this into our chambers. where we make the molecules to demonstrate such a scheme. Another thing that's actually relevant is, perhaps not for scheme, perhaps not for interaction, but for detection. If we don't have this molecule here, this atom here could also, in a way, serve as a way to read out in a non-destructive way the state of the state of the atom. The state of the molecule. So this could be a good way also for these kind of bioalkali molecules, where we couldn't just directly scatter photons. Okay, so let me so that's what I wanted to say about these molecules that we assemble from single atoms. And I want to say use a few slides to also talk about these calcium fluoride molecules, which are work done in John Doyle's lab, where we can, let me just directly go into here, where the experiment is now second generation, where we have this pretty picture of the apparatus, where we have basically the capability of much tighter tweezer than the initial demonstration. The glass out with large optical access, high voltage electrode inside, and compatibility with cryogenic if we want to shield out black body radiation and possibly also go into 2 dimensions. And the progress is very fast. Already, maybe not so much in detail. Now we can have a large number of arrays, for example, array of 60 single molecules. And these are really nice in the sense like when you can see the molecule directly, you can rearrange them. These are not rearranged, these are just average image at the moment. But they can be rearranged, and then we have shown that we can rearrange as well. The difference between these double sigma molecule and sigma molecule has it kind of sort of goes into these different structure actually has some advantage. I guess the technique overall has pros and cons, of course, for the 2 different approaches preparing single molecules. And these double single molecule, after one cools down, later cool down, and trapped in the optical tweezers, the typically, the population scattered in multiple internal states. So one has to prepare them ultimately in a single one from doing optical pumping. And usually it's a kind of optical pumping scheme to allow the molecule to go into a particular dark state, and then you blow away the rest, that's bright, and hopefully they're gone. And then your dark state will be your initial starting point to further manipulation. Now, the one nice thing, as you can see the structure here, is that these molecules have the electron spin. And therefore, these energy spacing, although I'm not really denoted here, are much bigger. So in terms of the speed limit that I talked about previously, pair states that you choose, the speed limit is not so much a speed limit because the energy levels are much more spaced compared to the nucleus being energy levels of biology. And there's also one very nice feature is that the light shift, the differential light shift that you would expect on tweezer, which will nominally again be very large, but you can find states, you have more states to choose. You can find states such as with n equal to 0, f equal to 1, mf equal to 0, and n equal to 1, f equal to 0, and mf equal to 0 state as the qubit state. And these opposite parity in terms of opposite rotation states, they both have mf equal to 0. So to the first order, they actually have they don't have first order light, which means in the case of, compared to the case of bioalkali, where we work really hard to try to cancel that out. To the first order, you don't have to worry about that. So that was kind of the limitation to get under control for the bioalkali. But here you don't have to worry about that to the first order. But you do still have to worry about it to the second order because these molecules are not as cold, and therefore it does sample more light variation, feature like tracking variation than you would for these bialkali where they're already in the motion. Okay, but that can be taken care of just by choosing the right magnetic field, right intensity, so that you kind of get some quasi magic condition as well. Okay, so for this, we can prepare molecules, array of them and then interact them pairwisely. Single body interactions, single body coherence time. So this is what I was telling you, first order not limited by like this, but second order it is, and then go to the magic condition. It helps with the spin echo, with the spin echo, the pulses is coherence time of 33 milliseconds, but one can use more sophisticated dynamic decoupling scheme, such as XY8, and then this could again also go up to sort of half of a second. And that's necessary here because the dipole, I guess I would say one, so the downside of choosing these states is that the effective dipole is a little less. I think the math one can work out, and I didn't work out myself, but so the dipole moment is less because of some additional geometric factor of the state that you choose, and therefore the interaction time, even from distance, is also slower. But for that, you don't have to work as hard for the light field. Okay, so as a function of separation, we see these coherent oscillations due to dipole interaction, which is actually quite amazing in the sense that these molecules are not cold, not as cold. And initially we didn't think we would see it because there's thermal motion and the dipole interaction is very sensitive to the separation, in the separation of the molecule. And because these thermal motion, the trap frequency are faster than these kind of time scale. So essentially that kind of average out, the thermal motion kind of average out, and therefore you still, eventually you have sort of motional rephasing in a way to not have to worry about the position. Ultimately, these decoherence, it does decoherence after a few oscillation is due to these thermal motion, but nevertheless, there is already oscillation that you could see. Okay. And on this plot, we can measure these oscillation, basically the oscillation time scale as a function of three-field separation. And it actually deviates from this sort of 1/r³ scaling that we expect. And this is due to the fact that the molecules are hot and then they're really sampling, more area of the trap than sort of this point. These 2 points are exactly at this separation. Okay, so perhaps let me just elaborate on that a little bit. Do I have, where's the thing? I have it until 11:20 or 11:15? Okay, yeah, okay, now. This. Okay, so there's sort of, to explore this sort of deviation a little bit more, we should talk about the angle of dependence. There is dipole interaction depends on not just the distance separation of the molecule, but also on the angle dependence of where the molecules are relative to one another and relative to their dipole interaction, the dipole axis. Okay, so first of all, we can change the orientation of the dipole by changing the magnetic field direction at the quantization axis here. And you can see that depends on if they're like this way or this way. This way we expect the dipole interaction to be twice as strong as the repulsive interaction, and so the blue is faster than the orange red. And at this 54.7 degree, which is the green, then you don't see complete oscillation because dipole interaction cancel out. And so these are sort of the angle, but at the same time, that allows you to kind of understand, if you have confinement in different directions, but they're relatively weak, and that the motion of the particle is, the motion is not stationary, it's relatively hot, then the distance between the distance between the two, the 1 over r cubed here, r cubed is not always the same if your molecules are hot and deviating from these axes. Okay, so this picture is trying to depict a different scenario that allow us to kind of explain the deviation from this 1 over r cubed scaling. Oh yeah, actually, I wanted to also mention that this work is done in parallel with the work that was done. Actually, first was demonstrated in Princeton, but very soon also in the case of calcium fluoride influence. Okay, so with that, we have dipole interaction. That means if we wait just the right amount of time, remember this pi over 2 time scale, for example, in this preparation, we didn't start like 1 and 0. We start with 0, 0, so we can do some, superposition preparation and wait, in this case, a quarter of a cycle, and that time scale is about 20 milliseconds. Then one can prepare belt states. Okay, so without going into too much details, yeah, the usual way that people demonstrate to check that you have belt state is that you prepare it and then you do a single qubit rotation in terms of arbitrary axis in our case that a single qubit rotation for one of the qubits, one of the molecules, and see these parity oscillation. It's in the EPR pair case. When you start with correlated spin, up, up, plus, down, down, and you want to measure their in different bases as opposed to just up, up, and down, down. This is effectively the equivalent of that, but not changing the basis that we measured. Okay, so from the contrast, and from these measurements, the parity, the parity of when you measure one, what if it's up and what's the state of the other one, up or down, these kind of tomography, you can get the bell state fidelity, and in this case, it's 0.3. Okay, so to claim really entangle, without any correction, this number has to be greater than 0.5. Okay, so then not yet, without here you cannot really claim that they're entangled just to these criteria. But we know the fidelity is actually much higher because it turns out this fidelity here is kind of reduced due to state preparation. So if we were to correct, it's higher than 0.5, but that's not sufficient because it has to be uncorrected. So it turns out the reason, that the state preparation, meaning these optical pumping, the states are not perfect, but there is a way to kind of to see, which shot we have prepared perfectly and which shot we have not prepared perfectly, and then excluding that, which is, legitimate. Then we can see, whether, therefore, we don't have to do any further state preparation correction. We just, if we know which shots are the ones that is mixed up with the state, not prepared perfectly, then if we have a way to detect that, we can throw it away. Then we can, we can just use the data that has the state that preparing the right state, and then see what the fidelity of the belt state preparation. Okay, so it turns out, in these cases, oftentimes, when you have effectively spin up or down, they are in different states, we detect only one of them. We detect up, for example, and down looks like dark. Okay, so and this way, sometimes you cannot distinguish between dark being down, or dark being that there's just simply no molecule preparing that state. Molecule is lost, or molecule is in the wrong state, and there is not a molecule in that right state, right? So this is convoluted, and that's sort of that's sort of the limitation. So how do we, so if we have a way to really turn that down, basically what we have to do is to turn that down spin to up an image and see, okay, it's really up now, or it's really empty. Then okay, if it's empty, then you just throw away that. You can post it like on that. Does that make sense? I mean, this is the kind of thing that we do a lot in optical tweezer often. If you have a way to detect in many stages, loading, for example, is one of them, and then state preparation. If you have a way to really detect whether you have successfully prepared the state that you want, then you keep that data, and then you didn't prepare correctly. You have some way of knowing that particular shot is not good, then you can throw it away. Okay? So we cannot distinguish between down track or down spin or empty track initially, but if we were to have additional pi pulse to basically flip the down to up, first we take an image, up, we collect, we know all the up, and then we do pi pulse from down to up. And if we see up, then we know it was down, and if we don't see anything, we know it was empty. Then we can throw away those empty tracks, okay? And then once we do that, then this is the data, and that bell fidelity is now actually the same as if we were to do, span correction. Span correction just means like, we know the preparation is inefficient, we divide by that factor. But in this case, we can distinguish which shot actually is prepared perfectly and which shot is not. And then this way, now this number is 3.5, and therefore we can go back. Okay, so with that, let me just say that with individual molecule detection and addressability to N plus now tunable dipole interaction for entanglement, then these molecular tweezers are now programmable in the sense that we can put in the Hamiltonian we want, and then do quantum simulation or quantum information. Of course, the real next step would be try to increase its fidelity. In the calcium chloride case, will be improved to actually implement nitrogen cooling so that these molecules are colder and the coherent oscillation can persist much longer. Okay, so I will just leave this one here, I guess, and I won't summarize, but I'd be happy to take any questions. Yes.
I have a question about your value polarization.
Yeah.
I'm just wondering how sensitive the compares time to the
Yeah. So well, I mean, I would say like the coherence time right now, it does not seem to be, for us, does not seem to be limited by once we're in the magic electricity, or even if we're slightly off, it's not limited by that right now, because you don't really understand where it comes from right now. But I would say the sensitivity, ultimately the sensitivity, yeah, so I guess what I wanted to say is that we would expect, we have reduced our light shift by 500,000. We would expect if that were to be the limitation to increase the coherence time by about 1,000, and that would be easily further effect. And then the sensitivity of the electricity, that angle is, we believe, is not. At least the way that we control it right now is not. So in terms of how well we can control the weight play angle in terms of efficiency, 0.01 degree is the diffusivity, or 0.1. 0.05, that would not be priced to the. Yeah, I guess I'd also say, this Annie and Gabriel are here, they're doing. They're confident.
Several ones I've been waiting for Chelsea before. Are there any other things that are obvious to develop?
We really the limitation, I mean, other things will be more like if we don't do these post-election, obviously the company better, so we don't have, the probability of two molecules returning the right state will be higher. But, the limitation that we really believe is the notion of. Yeah, and but I've been doing that for non-trivial for all of those stuff. So I mean, that's something that we're working on, but not, yeah. Hopefully something to show. So we'll have to see that, what, this is problem. Yeah, so I haven't looked into the number. Yeah, I mean, there's always fidelity on every single step. So that certainly would be a problem. But that does not hurt in this situation because we basically throw the data away, even though we shouldn't. As opposed to, you know what I mean? Like, so we did not include that. So it's like we just use it as opposed to things, so, or gaining, but we're not gaining that either. Because we just throw that data away.
Any more questions?
Yeah.
You were briefly mentioning like spatial fluctuations within the ITAMP traps. Can you compare like how strong are these spatial fluctuations from the array? You would expect the molecules are much heavier, so there's 0.5 less.
Yeah, so these are not 0 point fluctuations. These are just like they're not cold. So in the calcium chloride, they're not cold, so they are literally, occupying motion of quantum state up to like 30.
And suppose they would be the motion ground state, how would they compare?
Yeah, so suppose, so that still to be calculated, like to the first order, I would say they're in the motional ground state. Then you kind of think of it as an average effect, and therefore there is no decoherence. But okay, but then you have to say like, okay, how big of a effect that would be there, like this part of the wave function versus that part of the wave function is different dipole interaction, I guess one can calculate. So like, to the first order, I can say like that's in the single quantum state, I just average the whole thing and I just my dipole interaction. But I think the next order is that you probably have to like, somehow you could spread out a long distance, you could differentiate the molecule, you could differentiate molecule here versus there, and therefore, I mean, it does give a patient that one. Yeah.
We'll have an encore lecture tomorrow.
That's right.
So you can, and also on the bus, you can, okay. So without further ado, join me in thanking Kang-Kuen for the presentation.
Very small break so that we can bring some
Online.
I guess we'll have Nick.
Yeah. You're going to bring yours?
either way,
Yeah, if you have it connected, yeah, Nick is already there, so
yeah,
if you have enough juice in your,
now I put.
Okay, okay. yeah, so we'll use Kang-Kwen's, yeah.
Nick, are you there?
Hello.
Is he connected to the owl? Looks like,
Well, he could share, I mean.
yeah, he has to share, yeah, over here it is, yeah.
Yeah, he's there.
As he connects,
No, he is, let's see,
Hello.
just had two strings, yeah.
Oh, yeah. Oh, good. Good for others to see. Nick, you can hear us, right?
Yes, I can.
We're
Okay,
taking
excellent.
a few minutes break.
Yeah.
I'll be here, no rush.
So, yeah. Well, I mean, always on.
Yes. Good to know you. In Arizona, when there is always even a non-zero probability that there is sun at night. This is more or less the first time we were seeing the sun for real now. So another tradition at the visitor school, of course, is the group photo in front of the biosphere, which I'm sure you've seen in the book that went out there. That's what we're going to do right after we finish. And Nick is hearing us. We will Photoshop him into the photo. He's not here. So we will, after we finish the lecture, the next lecture is over, we'll go and take photos
And then we will disperse into the seabed to change the things and come and grab our lunch and go to the parking lot. Okay? The bus will be before 1:30. You're not there? So that's the plan. Right. Nick? Nick? Hello? Still? Oh, hi, Nick.
Hello.
Take it over.
All right. All right, welcome back. As a reminder, you can find all the slides here, including so first I'm going to wrap up some slides from last time, and then I'm going to move on to some new slides, which are all posted here on our group website if you're interested. So last time, this is where I left off last time, and this sort of maybe shows a sort of summary of some of the like polyatomic, some of the things you can do with polyatomic molecules, laser coolable polyatomic molecules. You can laser cool them. You can polarize them in small fields. You can tune their electric and magnetic moments, and all of which are very useful for CP violation searches. So this is an active area of research. So this is where I ended up, and so now I'll continue right where I left off. Oop, wrong way. Maybe I'll start by disclosing a downside. I think I disclosed some earlier. They're more complicated. They have more modes. They have more leakage channels. They're generally not dramatically worse than diatomics. You have maybe like two or three more leakage channels. Times more leakage channels, or so. But there's another aspect which I think we didn't really appreciate when we started working with these things, is that there are complicated interactions between this orbital. So remember, little l is the vibrational angular momentum for this doubly degenerate bending mode. The sort of middle nucleus can kind of orbit around the symmetry axis in one way or the other. So there's angular momentum with a projection on the internuclear axis. And just to go back a little bit, we talked about how that was actually very useful, because that is kind of intuitively what gives you this parity doubling and high polarizability. So this angular momentum around the symmetry axis is very useful, but it can also give you some complexity. So I guess with the electromagnetic moments, we saw it gives kind of good complexity in a sense. It gives like tunability and controllability, but it also gives you some unwanted complexity in a sense. In particular, this angular momentum interacts with the electronic orbital angular momentum L, if there is any, in very messy ways. There has to be electronic orbital angular momentum. So for example, a doublet sigma state that's bending actually is a pretty easy state to understand. It really just looks like a regular old non-bending doublet sigma molecule, but with the levels split by parity doubling. So the structure is not too bad. However, if you have electronic pi or delta states or higher angular momentum, electronic angular momentum states, states that have both electronic angular momentum and bending angular momentum are a total mess. And there's almost not like a unified description of them. I guess there are some kind of general principles that describe how they look. And so this is generally sort of called vibronic effects. So, vibronic is like vibrational and electronic. These vibronic effects result in splittings between states. They result in mixing between states. So for example, if you have a doublet pi electronic state, spin orbit, just regular old spin orbit, just like in atoms, splits this. The interaction of L and S splits this into two fine structure components. But then if you have a bending molecule, these are further split. Each of these is split by the interaction of big L with little l into 4 states now. And these states are all very complicated. They look very different. And they often are very heavily mixed and very perturbed. So you get just more, messier interacting perturbing states. And it can get really out of hand really, really fast. And it turns out that if you want to understand vibrational branching on the kind of 10⁻⁴ level or better, which is what you need if you want to do like magneto-optical trapping or something, you have to understand these vibronic effects very well. Even if you're not really including any sort of bending mode states in your cycling scheme. And that's because even like non-bending states, like these 000 kind of non-vibrating at all states in the two different fine structure components of a pi state, they actually have mixings, higher order mixings with these bending modes that kind of borrow some character from these other states and change the branching ratios. These effects are very small in an absolute sense. They're kind of 10⁻⁴, but you need that level of understanding. And so this is theory work that has been kind of really refined over the last few years, largely motivated by laser cooling polyatomic molecules. So a lot of these molecules, these days, there's very powerful ab initio theory that allows us to model molecular structure on the computer very well. So you can get all the states, for say this, I think this is calcium, possibly strontium, OH. You can get kind of wave functions and orbitals for all the excited states, but also you can get, here is a very big, impressive table of vibrational branching ratios and vibrational energy levels, both measured and calculated. And there's, as you can see, there's kind of percentish level agreement between them, which is actually quite good. And in fact, black box methods. By black box, I mean things that don't require a lot of user input and are therefore in some sense kind of, easy to use. Things like DFT or coupled cluster can give you kind of 1%-ish energies, 1%-ish accuracy and on things like energies and geometries and branching. It doesn't give you these sort of higher order vibronic things. So like these, you'll see that, here, down to several, this last digit is kind of the 10⁻⁵ place. If you want to do something like that, you can't use a black box method. You have to use these kind of sophisticated vibronic interaction models. But even if you just ignore all that stuff and you just use these like black box methods like density functional theory or coupled cluster, you can get all this stuff to the kind of percent level. So it's pretty good these days. So thank you, theorists, for making all these really sophisticated tools, but then also like showing experimentalists how to use them in some cases. However, the experimentalists are not out of business because you still need to measure these things in the lab. 1% is pretty good, but 1% on top of an optical transition is still like terahertz of uncertainty. And so you can get terahertz uncertainty on transitions where the radiated width is like 10 megahertz wide or something. So you still have to go and measure these things because you not want to just know where the levels are and find them so you can shoot a laser at them and actually address them in the lab. But you typically want kind of sub megahertz information to do precision measurements or like microwave addressing and things like that. So you have to do spectroscopy. Generally, there's kind of a usual for these types of molecules, there's usually a two-step process. Hopefully step 0 is like you call your spectroscopist friend and convince them to do it for you. And like sometimes they say yes, but sometimes you have to do it yourself. So first you do broadband survey spectroscopy, like looking for these little tiny lines on top of these big uncertainties, or for molecules that are really complicated and poorly understood. you might not even know what's up there. You just have to search around and see what you find. And so first you do broadband kind of low resolution spectroscopy. So a common technique is called dispersed laser induced fluorescence, or DLIF. And the idea is if you have a scanning excitation, meaning like a laser. So you scan your laser over a very wide range. And every time you hit a resonance, it could be a broad laser, by the way. In fact, it's kind of nice if it's a broad laser, so that you can cover more area faster. Every time you hit a resonance in the molecule, you'll get scattering. And so you'll know like, oh, there's a transition there. But if you then collect the fluorescence and disperse it on a diffraction grating and then image the dispersed fluorescence on a CCD or some sort of camera, you can get the wavelength information for all these decays. So you've learned kind of in this one shot, you've learned a lot of information. You've learned that there's a resonance here, and you've learned there's a bunch of resonances at all of these. And you also, if you're careful about calibrating, you can even get the intensities of all these things. So you can get like branching ratios for what fraction of the time does this state decay down to all these different things. And so, this is a plot showing some real data where this was done. And you can see that this is for like a laser coolable, triatomic. There's a very strong line, which is the kind of main line. And then there are kind of some weaker lines for the more dominant leakage channels, like to the metal stretch. But then if you zoom way in, you can see a bunch of tiny little bumps kind of all the way down onto the sort of 10⁻⁴ level. So this gives sort of a very big picture of the molecular structure with kind of tens of gigahertz-ish resolution, kind of limited by this grating. You can only make broadband gratings that have so much resolution. But then once you've narrowed it down to kind of 10 gigahertz or something, you can go back and do narrowband precision spectroscopy using just things like absorption or fluorescence or like double resonance methods. So basically now take a narrow laser, scan it in your smaller region, and just see when you see, blips of one type or another. But in reality, this usually takes years. So, you can summarize it into bullet points, but just because molecules are so complicated, even simple ones, people who work with them tend to spend a lot of time just doing spectroscopy. But, it's getting faster though. So something I alluded to last time is other structures. So I've spent most of the time talking about these linear triatomics, mainly because, well, they have 3 atoms, so they're the simplest polyatomic. The fact that they're linear makes their structure very simpler, so they're kind of very easy to understand, or they're the easiest polyatomic molecule to understand. But at the same time, they also have kind of all the features that make polyatomics interesting. But there are other features that other structures have that are also interesting, or maybe more interesting, or differently interesting. And one is symmetric tops. So a symmetric top molecule is something like like a metal OCH3. I probably should have had this graphic come up first. A lot of the story is very similar, like that metal, for example, if this is something like calcium or strontium, it inherits the laser coolability. If it's something heavier, like strontium or barium or radium or something, terbium, it inherits the fundamental symmetry violation, exactly the same as the OH or the fluoride molecule. But now there's a difference, both with diatomics, but also with even the linear triatomics. Now the parity doubled state is a rotational state. It's not an excited vibrating state, it's an excited rotating state. So here's a symmetric top molecule. So it has this one is calcium, although it's kind of the same for any of these alkaline earth type metals, O, C, and then HHH, H3. And in this case, so there's also like a bent state, which has exactly the same parity doubling. But there's also now in the ground electronic and ground vibrational state, there's a rotational state, which is parity doubled. And it arises from some sort of angular momentum projected on the axis, which in this case is just rigid body rotation of this H3 group around the symmetry axis. It can rotate one way or it can rotate the other way. So you get angular momentum on the axis, and so you get parity doubling. In this case, it's called K doubling. K is this projection on the internuclear axis. And there are some advantages to this. So one is the splittings are smaller, so the parity doublets are even more closely spaced. They're typically like a megahertz or even less, in some cases as small as like a kilohertz. And because they're very low-lying excitations, and also it turns out kind of have different symmetry than their lower-lying states, they have a very, very long lifetime. Like hours or something, days, very long. Another difference is that, and this is sort of a complicating difference. I guess it's, there are good sides and downsides. You have identical particles in this molecule now, which are these nuclei, these 3 hydrogen nuclei. The nuclear spin wave function has to obey Pauli statistics. And so that means you end up getting 2 nuclear spin isomers. Like, are you in sort of a singlet or a triplet? I shouldn't have said singlet or triplet because it's like, it's 3 spin halves, but it's basically like the 3 different ways you can combine the 3 spin 1/2 nuclei for the overall wave function of the whole molecule to respect Pauli statistics. You can only have sort of different symmetric and antisymmetric combinations of these nuclear spins. And because rotation also has, and that tends to be very strongly coupled to the rotation of the molecule as well. And the reason that's a complicating factor is not just because, well, I guess it's more complicated, but also these 2 nuclear spin isomers, you basically need to address them individually. So you sort of have to add new repump lasers to address sort of the K = 0 and K = 1 states. So for example, this is from a paper, laser cooling one of these molecules, calcium OCH3 at Harvard in John Doyle's group. So you have to add some more lasers to address these new states. So, as always, like you get more features, but with more complexity, but you also get more complexity with more complexity. The mechanism, earlier we talked about how both lambda doubling or omega doubling and L doubling arose from some like moment of inertia difference between just basically, you lower a symmetry, you get 2 different moment of inertia, you get effectively sort of a slight difference in rotational constant for the 2 different states, which effectively splits them. And in principle, things like that are at work here, although it turns out that the dominant mechanism is something called anisotropic hyperfine, which is kind of neat. It was first understood in like the 50s. So this is a figure from a very old paper, this bottom one. And the intuitive idea of where this comes from is you have these 3 nuclear spins, the 3 H's. They have to be symmetrized or anti-symmetrized, depending on the overall the symmetry of the nuclear wave function. But that means that because they're symmetrized or anti-symmetrized, you end up, if you look at sort of the wave function of those the nuclei, like where are the nuclei spending time, they end up in sort of cosine and sine like patterns. Very, very much like the lambda doubling argument we went through, except now it's not the moment of inertia that's kind of giving you the dominant contribution. It's the fact that now these different shapes, different distributions of nuclear, of the position of the nuclei, which have magnetic moments, those interact with the electron spin or the nuclear spin. If it's like a closed shell molecule, but if it's something like, calcium or strontium or something where there's an unpaired electron spin, the nuclear spins, the nuclear spins on the hydrogen will interact with the electron spin just through like dipole-dipole. But now there's a shape dependence of the dipole distribution, which is correlated with the kind of parity state of the molecule. And if you make a back of the envelope estimate of like kind of what's the dipole-dipole interaction of something, you know, roughly a Bohr magneton and roughly a nuclear magneton over whatever this distance is, it ends up being about 100 kilohertz, which is pretty close to what it is actually, you know, observed to be in these open shell, like laser coolable, you know, OCH3 type molecules.
I think I have a question.
Yeah. I heard. Let me put my headphones in here.
So can you hear me?
Yes.
So this +1 and -1, I guess I kind of see your arrow, you know, the direction is spinning. And then the bottom one where the bottom one, you're looking along the z-axis, is that what? Sorry, the middle panel picture, is that, are you looking along the z-axis?
Yes.
Okay, and that's why X and Y are different. So you're basically, one is lined up in X and the other one is Y.
Yeah, that's right. Yeah, so that's a little confusing that, yeah, this view and these views are sort of different. This is a side view. This is like a kind of top view. Both of these are like top views. And so that's why here, this is like the electron spin here, which is kind of like right in the middle. And then the nuclear spins from the H3s are, you know, off of this symmetry axis and have these different distributions.
And I guess these hydrogens are fixed relative to that, that's why it's not the same between the +1 and the -1.
Yeah, so good question. That's another kind of misleading thing with this slide, is that these are showing the distributions of the hydrogen nuclei in parity eigenstates, like the free field eigenstates. These are not the parity eigenstates. These are the like fully polarized eigenstates. The free field eigenstates, analogous to this, the free field eigenstates are actually superpositions of these. The polarized eigenstates are ones where kind of the K or L or whatever is kind of well defined in the lab. In zero field, they're superpositions, similar to the same with like the omega doubling or L doubling, right? Like the parity eigenstates, free field eigenstates are superpositions where the projections are one way or the other. And so you end up getting this like sine and cosine distribution. And it's the same thing here. The free field eigenstates are actually superpositions of these, which is why you get these two different patterns.
These are the parity states shown in the middle here.
So in the middle, these are the parity states you're showing.
Yes, right. These are the parity states. These are not the parity states. The parity states are superpositions of these, you know, the even and odd superpositions of these.
In those pictures, the hydrogen triangle seems to more or less rotate with that. So why are they different?
The hydrogen seems.
There's a triangle with H at the corners.
Oh, I'm not sure if the position of these three H's is sort of physically meaningful in this picture, or if it's just kind of reminding you that that like what you're defining, basically kind of giving you the definition of this angle. So I'm not sure how to interpret this kind of triangle here necessarily.
Okay.
Yeah, for me, the part of this that I sort of know how to interpret is this here, which is giving the wave function of the positions, you know, where the hydrogen nuclei are spending their time in some sense. So yeah, any other questions about this slide? Oh yeah, I guess there's one more point. I guess I already said this. Yeah, this is very analogous to these other doubling mechanisms, especially like lambda doubling, but now it's from spin-spin interaction, not a moment of inertia, thing. There's an even more complicated type of molecule, which you can look at, which is asymmetric tops, which basically have like kind of no symmetries in some sense. Or maybe they have a planar symmetry or something. But they have 3 distinct moments of inertia. They don't have any kind of degenerate moments of inertia like a symmetric top or a cylindrically symmetric molecule would. And the short answer, I won't say too much about these other than they're very, very complicated. Just even like looking up, like what's the rotational structure of one of these states? Just because there are so many, there are multiple rotational ladders because of the different moments of inertia. There's a lot of mixing between them. There's now, you get sort of additional splittings because, for example, now things that are nominally degenerate in cylindrically symmetric molecules, like are the electron lobes, like the pi lobes for an excited electronic state, are they sort of this way or this way? That's kind of a degeneracy for like a diatomic, but when you have, say, a bent molecule giving you some symmetry breaking between these 2 directions, now these 2 states are kind of distinct electronic states. So I won't say anything about their detailed structure, largely because I don't really understand it. However, surprisingly, these appear to maintain their laser coolability. Like this sort of metal localized bond decoupled from all this other stuff seems to hold. Nobody's laser cooled a molecule like this yet. But this is sort of a research frontier. These could be potentially even more advantageous for things like CP violation searches, just because they have more and different types of doublets that just might have better features for experiments. But this is something that people are kind of in the middle of thinking of. And so that kind of ends. I'm gonna end the like polyatomic discussion there. I did have a section about other bonding motifs, which I won't go through. But the idea was that, so far I've talked about things in this column. It turns out you can also come up with motifs where you can get sort of photon cycling with things in different columns by relying on sort of different bonding mechanisms and features. But since I said I won't talk about it, I actually won't talk about it. If you want to learn more, ask me sometime. So instead, I will switch. Actually, are there any questions about the, like lecture 2, the polyatomic stuff, before I switch to lecture 3?
Go ahead. Just continue.
Yeah, I'm pulling up the other PowerPoint here. All right. Welcome back to lecture number 3. This one is shorter, so I might be able to get through the whole thing. We'll see. So right now, for this one, I want to focus on some aspects of nuclei and how you can study them with molecules. In particular, I talked a bit about like electron EDM. There are other symmetry violating moments in molecules that you can observe, which arise from the nuclei. So the electron is sensitive to new physics that couples with the electron, but it's not necessarily sensitive to, say, things that couple with like quarks or gluons or something. But the nucleus is. There are 2 CP violating observables that arise from the nucleus that you can look for in molecules. One is a nuclear magnetic quadrupole moment, and the other is a nuclear shift moment. And I'll say a little bit about both of these, and then how you'd go about looking for them. So I'm going to focus on these two here. And yeah, so it turns out all the methods used to look for all of these are very similar, but the type of science you can explore is different. So so to remind you, to go back a bit, something that Dave talked about earlier, observing, I guess, any EDM, not just nuclear EDMs, in atoms or molecules is complicated due to Schiff's theorem. So that's an observation that atoms, I guess it should be atoms and molecules. Atoms and molecules don't accelerate in static electric fields. Therefore, the average force, which arises from electrostatics, has to be zero in steady state. And therefore, the average electric field experienced by the constituents will be zero. So in other words, charged particles will always move to a point where they see zero average field. So, that's how ion traps work. And this is true, as stated, this is kind of strictly true, but there are evasions. One, which I won't say anything more about because I'm not going to talk about electrons. The fact that electrons move relativistically means that even though they may see zero electric field, their dipole moment, like Lorentz, contracts. And so the average interaction of the dipole moment with the electric field is not necessarily zero. These relativistic effects. So it's a relativistic effect that is dominant near the nucleus, which is why we care about the electron wave function near the nucleus that I brought up a couple times before. For nuclei, the primary evasion is that they have very complicated shapes. They're not like point particles, it turns out. So nuclear shift moments arise from the fact that the charge distribution in a nucleus, which comes only from protons, but also the EDM distribution, which can come from protons and neutrons, they need not overlap in a nucleus. So the charge and the EDM distributions might be slightly offset, meaning that you get some kind of residual charge distribution near the surface of the nucleus, which kind of looks like a dipole moment. It's called a nuclear shift moment, and it arises from a mismatch between the charge and mass distributions in a nucleus. Intuitively, it turns out there's actually a lot more complicated stuff going on under the hood, but this is a really powerful way to think about it. And because it depends on kind of the details of the nuclear shape, as I will discuss later, these can be significantly enhanced in non-spherical nuclei with very deformed shapes, so that these kind of mismatches can be very large. The nuclear shift moment looks like a charged shell with a dipole-like distribution. Again, this is from this kind of intuitive picture of it being kind of a charge EDM difference. It looks like a residual shell with some dipole-like distribution, which means that it creates an internal electric field effectively in the nucleus, which is aligned with the nuclear spin, and which is P and T violating. So the existence of any sort of electric field aligned with a spin, like a nuclear spin or an electron spin, violates a whole bunch of symmetries. And then the mechanism is that this internal electric field, like at the nucleus, will mix S and P like atomic orbitals, and therefore induce an EDM in the atom or molecule. You don't need unpaired electron spins for this, but you still need electron density at the nucleus. So the electronic structure still matters a lot, even though you kind of aren't probing the electron, you're kind of using the electron to like amplify the effect of this moment. And so you still want electron wave function density at the nucleus. Even though you're not looking for an electron EDM, it turns out you sort of always want that for all of these symmetry violating moments, even though the reasons are very different. the electronic structure requirements end up being basically the same. But since you don't need unpaired electron spins, these are often done in diamagnetic systems, just to reduce magnetic sensitivity. If you don't need that extra unpaired spin, you may as well just not have one because it'll just pick up magnetic field noise. Since this is a moment that's correlated with the nuclear spin, you have to have a non-zero nuclear spin. Otherwise, you can't have an observable moment like this. So you need a nuclear spin of at least a half. And then the Hamiltonian that you're looking for is basically an external electric field, interacting with this nuclear spin, more or less. What you're really looking for is this external field interacting with the induced atomic or molecular dipole, which is proportional to this. But at the end of the day, this looks very much just like an electron EDM search. You're looking for a splitting between like a nuclear spin up and down instead of an electron spin up and down. So these experiments look very similar. These moments, nuclear shift moments, can be enhanced very dramatically in nuclei with an octopole deformation. So what does that mean? So the nuclei have basically constant density. However, the shape of their surface doesn't need to be spherical. If you take the shape of the surface and expand it in spherical harmonics, something with an octopole deformation means that this beta 3 term, so the third order spherical harmonic contribution is not zero. Quadrupole deformation, it refers to beta 2, and I'll talk about that later. But so octopole deformation means that the nucleus is shaped sort of like this. So this is a recreation of the radium-224 nuclear shape based on experimental measurements. And you can see it's pretty dramatically distorted. People would usually say this has a pear shape. So people often refer to these as pear-shaped nuclei. And it turns out this is not very common. And it's not very common, and it can be even hard to determine whether nuclei have these. However, the places where they're sort of known to exist, either by direct experimental measurement or by very convincing theoretical data, is kind of 2 regions, accessible regions, meaning quasi-stable nuclei. These ones are not very stable. These are not very stable. But actinides and rare earths, there are some pockets where there are nuclei with octopole deformations. And in particular, these actinides are interesting because for symmetry violation searches, you want the species to be very heavy. All of these sensitivities scale very rapidly with the proton number in the nucleus. So things like francium, radium, actinium, thorium, protactinium are up here. They have these large deformations. They're heavy, so they have really high CP violation sensitivity. But that also presents a challenge, which is that they're heavy radioactive species, and they're all short-lived. So they all have, none of them are stable. And at least it turns out for the spinful isotopes of these, which you would need to really make use of this effect, their half-lives are typically in the order of like days or weeks. So it's challenging to work with them. But there's a lot of interest in working with them because you can combine the nuclear shift enhancement is sort of an intrinsic enhancement in the nucleus itself. You can combine this with, I should say, atomic or molecular enhancements. But in particular, if you combine this with molecular enhancements, so the fact that like molecules have very large, in extreme electromagnetic field environments that amplify these CP violating moments, you can get very large sensitivity gains, say like 10 to the 5 or 6 for a molecule containing a deformed nucleus versus say an atom with a spherical nucleus like mercury or xenon. However, on the other hand, mercury or xenon, because they're atoms and because they're not radioactive, you can use very highly advanced, sophisticated experimental methods. So these experiments are exquisitely sensitive, and so they're they're very hard to beat, even with these, even with these gigantic enhancements. It'll still be hard to kind of overcome the atomic spherical nuclei experiments. However, as I'll say a little bit more about later, because there are many different sources of possible CP violation, especially in nuclei, you actually need multiple experiments. So these aren't, it's not sort of like one of these is going to measure what we want and then we're done. It's like we actually kind of have to measure something in all of these systems to actually back out what the underlying physics is. And as a side note, I guess I'll say a little bit more about this later. Truly exotic nuclei like protactinium-229 might offer another factor of 100 or even 1,000 on top of this. So now you're talking about like 10 to the 9 sensitivity gain, although that is still kind of unproven. So why does this shape give rise to this big enhancement? It turns out you can draw a lot of parallels to things that we've been talking about. Me and Dave have been talking about. In the absence of any like fundamental symmetry violations, in equilibrium, in free field, in steady state, this octopole shape, the nucleus should be in a superposition of these two shapes. So you should end up kind of like a molecule, right? In zero field, a polar molecule is in a superposition or a rotating state where there is no reflection asymmetry. You end up with a nice reflection symmetric thing, say like this. So you end up with a superposition of these octopole shapes. You get a nice non-symmetry violating nuclear shape on average. So everything's fine, no symmetry violations. However, if you have symmetry violating nuclear forces, it can mix these two states. So you can end up with your actual nuclear state being some slightly asymmetric superpositions of these two states. And so you end up with some residual asymmetric reflection, asymmetric shape in the nucleus. And this is nice because now remember this nuclear shift moment was kind of something that depended on sort of the surface of the nucleus in some sense. Now the surface of the nucleus is a big mess. And so these kind of mismatches between charge and mass distributions can be just intrinsically very large because of this messy shape. So for if you formally write out what's the shift moment in a nucleus, it depends on this kind of internal shape. Like this is sort of how deformed is the nucleus, how large is this beta 3 octopole deformation, and then how large are the CP violating, PT violating forces that mix them. And then it's some kind of, because you're talking about mixing states through weak forces, it's some kind of perturbation theory expansion where you divide by an energy denominator. But there's kind of another enhancement, which is that in deformed nuclei, because this mass distribution kind of looks like a rigid rotor, and it turns out that it is. So the nuclei that have this shape actually have a rotational ladder of like rotational nuclear states with opposite parity. And so you get low-lying states of alternating parity. So this sum ends up just being kind of like one term, and also large. So you get a whole bunch of enhancements here. So you get the fact that just the intrinsic shape of the nucleus is very messy. The fact that the shape is, so that makes this big. The fact that it's kind of a messy asymmetric shape gives it like a rotational type structure, which pushes this down. So this goes down, this goes up. And then this is kind of the thing you want to measure, like the undiscovered particles and forces. So that's kind of why the enhancement in these molecules is so large, because it's a compound enhancement from a few different things. So for example, here's the energy levels according to experiment of the radium-225 nucleus. You get some, you get sort of a ladder of rotational states. The order is a little messy because it's, it's a nucleus. It's actually very, very complicated. However, there's this fairly low-lying, at least for nuclear standards, this low-lying opposite parity state, which is only 55 keV away. For something like mercury, that's kind of 10 times or so higher. You get close-lying states of opposite parity. It's about 55 keV for radium, and it's basically parity doublets again. This doesn't quite look like a parity doublet just because it's kind of so mixed up. But it's still kind of the same idea that you have parity doublets, which we know are great in molecules. It turns out they're great in nuclei too. And so this gives you not only a larger enhancement, but a smaller uncertainty, because the theory is much, much easier in the sense that you only have to kind of contribute this one term. You don't have to sum over a whole bunch of excited nuclear states. You really just have to sum over like one. And this is important because the uncertainties for like spherical nuclei on nuclear shift moments can sometimes exceed 100%, meaning that like the error bars of the coefficient that you're trying to compute like includes 0. So you just just because the theory is exquisitely hard. But for something like this, the theory is much simpler, and and the effect is larger. Or I shouldn't say the theory is simpler. The calculating these sensitivity parameters has much lower uncertainty, and they're much bigger. And so the reason that 229 protactinium is so kind of unique, and there's a lot of kind of excitement about it, is because it's suspected that this opposite parity splitting in protactinium is like 50 eV, so very, very anomalously low for an opposite parity state. Maybe I should probably have had a bullet point on this. This is kind of an aside. People may have heard about how there's this nuclear state in thorium-229, which is in the like optical range. But that isn't to an opposite parity state. That's some kind of spin transition. So it's not relevant for nuclear shift moments, although thorium has a pretty big shift moment enhancement anyway. Another way, so shift moments can evade this shift theorem and give you observable symmetry CP violation in the nucleus manifested in an atom or molecule. Another way to evade Schiff's theorem is just forget about electrostatics, just use like magnetic effects. Magnetic fields aren't screened because there are no magnetic monopoles probably. So CP violating magnetic moments in the nucleus are just not screened. They don't suffer from this Schiff's theorem issue. And so here's an intuitive explanation of one type of magnetic effect that you could get in a nucleus that violates symmetries. It's a magnetic quadrupole moment. If you imagine a nucleus with a valence nucleon, and that's orbiting around the nucleus, so say giving rise to a spin, nuclear spin. So if you have a spinning nucleus, say arising from an orbiting valence electron or nucleon, if that nucleon has a dipole moment, which would violate all these symmetries, as it orbits around, it would create a quadrupole moment. So an orbiting electric dipole creates a magnetic quadrupole moment. So here you would get a magnetic quadrupole moment correlated with the nuclear spin, which violates all the same symmetries as everything else. If you look at it in a mirror, it looks different. If you do time reversal, it looks different. So magnetic quadrupole moments, permanent magnetic quadrupole moments, violate all the same symmetries. So they kind of are probes of similar physics. The way this manifests itself in an atom or molecule is if you have something with an electron spin, an unpaired electron spin, that interacts with this magnetic quadrupole moment and gives you CP violating energy shifts. In this case, I guess just to define a magnetic quadrupole moment, or to define any sort of quadrupole moment, you need a spin of at least 1. Or in this sort of hand wavy argument, if you have sort of mechanical orbital angular momentum, which is giving you a moving dipole, you need at least 1 unit of angular momentum. And in this case, you get another enhancement from quadrupole deformation, or you get an enhancement from nuclear deformation, but now it's actually from a quadrupole deformation, not an octupole deformation. And that's because if you have a nucleus which is kind of stretched out with a quadrupole deformation, you don't rely on these like single nucleon contributions. You actually get sort of collective contributions from like inner shells in the nucleus. So you get roughly kind of an order of magnitude or so improvement in a quadrupole deformed nucleus. And the experimental approach is again very similar. You're basically looking for energy shifts as you reorient these different spins, like the nuclear spin and the electron spin relative to each other and relative to some external field, to look for symmetry violating energy shifts. And so to kind of recap these different places that you get enhancements, it's a little it's tricky to think about sometimes, because for these nuclear things, there are both kind of molecular enhancements and nuclear enhancements. For something like the electron EDM, you just get what I'll call the internal field enhancement, which is the fact that the electron sees a very large internal electromagnetic field. And it doesn't really care. I mean, in some sense, it kind of arises from the nucleus. But what I mean by you don't get any additional enhancement is that like the electron is the same in every atom or molecule. The nucleus is different in different atoms or molecules, and the nucleus itself can have more or less sensitivity to CP violation by having a larger or smaller MQM or NSM, nuclear shift moment. So if you use, you always get this kind of field enhancement if you're looking for these nuclear moments. So meaning like you want a heavy atom or molecule that's highly polarizable and has like core penetrating electron wave functions. But also if you choose the correct nucleus with these deformations, you can get another enhancement of kind of an order of magnitude or several orders of magnitude. And as a one slide summary of how you look for these, like comparing how you look for them, for electron EDM, you're looking for a splitting between the spin state and the internal field. For the nuclear shift moment, you're doing the same thing, except now you're looking at the nuclear spin, reorienting it relative to the internal fields in the polarized species, looking for some energy splitting. So it's basically the same. For an MQM, it's also basically the same, except now you're trying to look for the interaction of the electron spin and the nucleus. So you have to compare sort of two pairs of states where the nuclear and electron spins are sort of aligned or anti-aligned, and then compare them. But in summary, the methods are basically the same. And so for that reason, people often just call these things EDM experiments, even if you're not actually looking for an EDM. And also importantly, the shifts in all of these cases are proportional to the polarizations. You always need something that's very polarizable. And the reason you'd want to look for all of these things, or why some people might want to look for all of these things, is that there are actually many different sources of symmetry violating observables in an atom or molecule. So even for electron EDM experiments, you're actually not sensitive to just the electron EDM. You're actually also indistinguishably sensitive to a new symmetry violating force between the electron and the nucleus. So even for just electron EDM experiments, you need multiple experiments if you want to be able to distinguish between these two effects. And for nuclei, it's even more complicated because there's just a lot more going on in a nucleus. There are quarks, which could have EDMs. There are nucleons, which could have EDMs. There could be new symmetry violating forces between nucleons or between quarks. We don't know what the origin of this new symmetry violating physics is, so it could show up in kind of any of these, and different nuclei have different relative sensitivities to all of these things. So that's what like motivates taking kind of a broad search to look for these moments. More rigorously, if you write down all possible sort of symmetry violating observables in terms of some kind of like irreducible effective operators or something, there are 13 of them. So you can't, if you want to ultimately nail down like which of these, unobserved parameters is non-zero or what's its value, you can't just do one experiment. You have to do, a bunch of them. So you need multiple sources from like EDM experiments, nuclear experiments, everything. And the dependencies are generally complementary. So two different molecules or atoms usually have different relative sensitivities to these things or these things, or this thing. I literally won't go through this table, but I just put it in here in the slides in case you want to see. It's kind of a summary of like the different features and like, do you want them or does it matter for what kind of physics you're looking for and why? So feel free to look this up in the posted slides if there's ever some molecule you're like, ooh, would this molecule be good for like a nuclear shift moment search? It's like, well, check this table or call me. I promise I won't lie and say it's not interesting and then pursue it myself. So experimentally, some types of molecules, there are a bunch of different molecules you could use to look for these things. And one interesting example, which I'll bring up, is radium, because it's interesting and it's also sort of unique in the sense that the atom, its ion, and radium-containing molecules can all be laser cooled because it has the same structure as things like calcium and strontium. So all of these things I talked about with like laser coolable structure and core penetrating orbitals and whatever, like radium has all of these things. But it also has extremely large CP violation sensitivity, not just because it's very heavy. So you get just, intrinsically larger enhancements, even to things like the electron EDM. But it has this octopole deformation, which gives it a very, very large sensitivity to, say, a nuclear shift moment. Of course, the downside is it's radioactive. So even the sort of the longest lived isotope, which if you want to do an EDM experiment is the one you'd use, it's like 1600 years. So it's definitely long enough to work with in the lab, but it's dangerous. If you want a spinful isotope like radium-225 to do like a nuclear shift moment experiment, now you're talking about like a couple weeks. So it's getting tricky. However, because these enhancements are so extremely large, there's a lot of interest in pursuing these experimentally, and there's been a lot of developments over the past few years and over the last decade. So atomic radium has been used in an EDM experiment at Argonne National Labs, impressively, like laser cooled and trapped and everything. Radium fluoride is predicted to be laser coolable, and recent high resolution spectroscopy supports this claim. You can assemble radium containing molecules from laser coolable atoms. You can use radium containing molecular ions, or sort of radium containing polyatomic, laser coolable polyatomics. So there's just, there's a lot you can do with it. So one of the things, I'll say a couple things you could do with it, and then I'll wrap up since I'm approaching the hour. Let's say you want to do an experiment with radium, and let's say you wanted to do an ion trapping experiment. The reason is because why would you do an ion trapping experiment? Because the Gilla EDM experiment has proven that ion trapping is a very powerful way to do an EDM experiment, and with sort of small quantities. So they actually, compared to beam experiments, the quantities they use are much, much smaller, but you leverage long coherence time. So that seems like a good match to something like radium, which you don't want. You want as little of as you can possibly get away with in the lab. So it seems like a good match, but there's a A problem is that kind of, your radium just has whatever electronic structure it has. And it turns out that electronic structure for at least like diatomic molecular ions is not very useful for this experiment, for the sort of GILA EDM approach, where you ideally would like parity doubling, which is an important ingredient in in that experiment. For something like radium fluoride plus or radium hydride plus, you don't have that. You have a singlet sigma, no doubling, there's no lambda or omega doubling. And so doing that type of experiment in a radium containing diatomic would be tricky, but of course you can just use a polyatomic. So, going back to the stuff from the last lecture, you can always engineer parity doublets with suitable bonding ligands. Because radium is so sensitive and because molecular enhancements are so large, that even if you could work with like one of these molecules at a time, you could basically, reach and go beyond the frontiers of like nuclear symmetry violation. And so, and not just this one molecule, you can kind of choose different ligands to kind of tune to your experiment, depending on what type of experiment you want to do. If you want to do like a GILA style spin precession experiment, like for their EDM experiment, or use some kind of proposed methods, like using clock measurements or quantum logic measurements, you might want different parity doublings or different kind of excited state energies, etc. So you can look at linear or symmetric top or asymmetric top molecules and kind of tune these parameters around by quite a bit. And hopefully, match to an experiment that you want. And, by the way, this, Andrew JH's lab at UC Santa Barbara has made all of these molecules and some more and trapped them and sort of controlled them. So, people are moving ahead with this stuff in spite of the technical challenges of working with something like radium. So neutral species, I mentioned they're expected to be very laser coolable. So meaning like kind of 98, 99% branching ratios. So even better than, things like strontium or ytterbium, just in terms of branching ratios strictly. And there's spectroscopy that now kind of supports this theory. And it's sort of, it's one of the few instances where sort of complicated relativistic effects help. So like, why are these kind of more diagonal than some of their like lighter analogs like strontium or something? And it turns out that because of relativistic effects, as you go down the periodic table, like going from calcium to strontium to barium, there are some perturbing electronic states that get closer and closer and closer. And in fact, for barium polyatomics, they're so close that they kind of mess with the states and they're very severely perturbed in a bad way. But the trend reverses at radium and those perturbing states get pushed like way up. And so you kind of recover some of the diagonality you start losing as you go down the periodic table. So, go figure. And so the spectroscopy I mentioned, it's very impressive. There's only been one sort of short-lived radioactive molecule has ever been probed spectroscopically in the lab. And that's radium fluoride. And it was done with a very impressive, complicated setup at CERN. But nevertheless, despite the very high energy of the starting point, they were able to do high resolution spectroscopy on sort of a whole rainbow of radium isotopes, including, radium-225, the nuclear shift moment one, and radium-226, the electron ADM one. And, there's a lot of growing interest in sort of turning this into, cold trapped laser cooling, et cetera, like people have now done with a few non-radioactive molecular species. So, stay tuned. People are working on that. And this, going back to something Kang-Kuen asked about earlier, if you wanted to like dream, like, what would like generation 3 or 4 or something for these like ultra cold polyatomic EDM experiments look like? So let's dream. So these are all numbers that these features are all like, nobody can do these now. But none of these are like ridiculous. I think people would all agree that you could probably do this, in our lifetimes. 1 million molecules, 100-second coherence time, some radium containing molecule in with some kind of like a symmetric top or asymmetric tops. So you have very, very long lived state, science states, etc. That would give you access to like, PeV scale physics or like 100 TeV scale physics, even at 2 loops, in both like the leptonic and hadronic sectors. So looking at things that couple to electrons and quarks, you could beat the strong CP parameter limits set by the neutron EDM experiments by, orders of magnitude. And you could do this experiment in, I don't know, 10 years, 15 years. So it seems exciting that there's kind of a realistic pathway to get these like very dramatic improvements on these things, by leveraging the types of neat tricks you can play with molecules. And then there's even more speculative. There's like room to improve on this. You could start thinking of doing like quantum enhanced metrology. Like these numbers are based on just like, the uncorrelated shot noise limit. No sort of spin squeezing or anything, which like, how would you do that? I don't know. Or, replacing this with some really exotic nucleus like protactinium. So, there's a lot of fun to be had maybe in this kind of weird radioactive molecule area. And if you're interested in learning more, you can visit this website with this really great logo. If you want to learn more about physics with short-lived atoms and molecules, because people are kind of getting interested in this sort of thing. And yeah, that was the last slide. So I will thank you for your attendance and apologize again that I couldn't make it, and ask if there are any questions.
Nicely done. So, questions? We have a few minutes before we go for group photo. So maybe on the light side, can I ask a question, Nick? If let's say radium fluoride device for sensing is developed, but there's sort of a half-life of, what was it, a few weeks or so?
Yeah, so the sort of nuclear sensitive isotope is 2 weeks, but the isotope with no nuclear spin is 1600 years.
All right. That answered my question. Any other questions? Renee? I think everybody's looking forward to the hike. I think they're all hiked up. So with that, any further ado, thank you very much, Nick, for sort of being here, although I'm sure that you wanted to be here.
I did.
We'll have to deal with your plane ticket later, because I think Jacqueline will be in touch. Okay. All right. So if not, then join me in thanking all of the lecturers today, including Nick. Take care.
Bye.
Now. So we're going to go then now. You may be able to keep your stuff, but we're going to go to the right here. Not down, obviously. And go.
Yeah.
How much battery do you have left?
Now I have 100
100. Oh, good for
because
you. You know, the other day when I ran, at the end, I was down to 2%.
Well, did you,
So there's a problem with yours then.
I think my battery's gone.
well, but was power or no?
It was powered, but it just didn't roll.
Just, yeah, was it plugged in?
Oh,
Find out.
because I had without,